Hey, hi. Good afternoon, everyone, and welcome to Energy Recovery's inaugural webinar for our region. My name is Ashik, and I'm the Business Development Manager for ERI handling the Southeast Asia region, and I'm based in Kuala Lumpur, Malaysia. Along with me today is my colleague Ajay, who handles India and Australia, and he's based out of Pune in India, as you might know. Just before we get started, I just want to go through some webinar-specific points with everyone. Firstly, please feel free to type in any questions that you may have in the Q&A tab at any point during the webinar itself. We will be collectively addressing those questions at the end of the webinar. Secondly, there are a few simple poll questions that will be displayed on your screens during the webinar. Please do answer them, and I imagine for the type of crowd that we have here today, it shouldn't take too much thinking. Today, we will be going through a very unique problem in the water industry at the moment, which is what is the cost of doing nothing? What I mean by that is what are the consequences of us in the water industry overlooking the utilization of ERDs in our RO systems? Whether it's low pressure brackish water systems, high pressure desalination systems, or even ultra high pressure ZLD systems. These RO systems are some of the highest energy consumption contributors to any water treatment cycle, especially when you look at it over the entire life cycle of the plant. Next slide, please. So going through our agenda here today, we will get things going with a brief introduction to energy recovery as a company before diving into the actual topic of the day that Ajay will present, including actual case studies and a few of the solutions that we have. Following which, we'll go through how do we actually provide quantifiable numbers in terms of energy savings and the CO2 emission reductions by utilizing ERDs. Finally, we will tackle the problem of, is it too late for an existing facility? And how can we help retrofit existing RO plants to achieve various final objectives that our partners and clients may have? Post switch, we will end with what I hope would be an interesting Q&A session with the crowd that we have here today. So I hope you have your beverage of choice ready and we can get started. Over to you, Ajay.
Yes, thank you. Thank you so much, Ashik, for the introduction, and good afternoon, everyone. Once again, thank you for being part of this webinar, and thank you for your time. Energy recovery devices have come a long way, and right from seawater desalination to reuse to MLD or ZLD RO application. And this webinar is very important and paves the way for what energy efficiency means to the plant. Next slide, please. Now, many of you know energy recovery. Energy recovery is a market leader in this space, and we continue to develop products which are relevant to evolving market needs and even the challenges that we are facing today. So I am Ajay Bajaj. I am responsible for India and Australia region, and I will take you through the rest of the webinar. And as we go through, I think it is important to know the company Energy Recovery, that what product and solution we are developing and how these products and solutions can help you. Next. Now, let me briefly introduce who Energy Recovery is. Now, Energy Recovery is a global technology company, manufactures high-performance energy recovery solutions for the reverse osmosis process. For more than 30 years, our core expertise has been pressure exchanger technology, which has helped the customers around the globe to reduce the energy consumption in seawater desalination plant. Now, this is where we have established ourselves. Our objective is very simple and straightforward. Help the customers to produce more water while using less energy. ERI was established in year 1992 in San Leandro, California, and became a public listed company on NASDAQ in 2008. Our state-of-the-art manufacturing facility is located in California, as you can see on the map. And we have recently announced a new manufacturing facility in Saudi Arabia. But together, both these operations bring ERI close to our customers and strengthen our presence across the globe. Today, thousands of pressure exchanger devices are installed, operated globally, and are working in many demanding applications across different geographies across the globe. You can see those yellow spots on the map. These are nothing but the installations that energy recovery has. Now, apart from the technology, ERI also supports the customer in all key markets through experienced sales, technical, and field services supports backed by the local teams with global expertise. So whether you are a consultant, whether you are an EPC company, or you are an end user who are looking to reduce the operating cost, this is the technology you should go for, and it has a long proven track record behind it. Next one. Now that you have known about the company, now let us look at what product and solutions we offer. Our product portfolio is divided into two parts. One is energy recovery device and other one is the pump products. Now, many of you know energy recovery through the product called pressure exchanger. Now, our products are, goes well beyond the single product, and pressure exchanger is first one of them. And this remains one of the most efficient energy recovery device in seawater desalination space, achieving peak efficiencies up to 99%. And it also has very high industry leading uptime of 99.8%. Now, these technologies are expanded to cater the modern challenges that we are facing. And we have now the economized version of pressure exchanger. We call it low pressure PX. The standard PX that you all know, that is what we use in seawater desalination, that is standard PX designed up to 83 bar. And we have ultra high pressure PXs for all the RO and NF applications where we can even handle the pressures up to 124 bar. Now, the other type of energy recovery device that we have is turbocharger. A turbocharger is a centrifugal type of energy recovery device. And nowadays, the use of turbocharger is very niche. This is used in some cases where there is a high pressure interstage boosting is required. Now we'll talk about the sweet spot of the turbocharger and even the pressure exchanger in coming a slide later in the presentation. Now, apart from it, we also have pump solutions. Now, in the pump solution, ERI also provides high pressure pumps, centrifugal and axial piston type in high grade material of construction for the RO and NF application. Besides, our product portfolio also includes high suction boost-up pumps or circulation pumps, which are very seamlessly integrated with our pressure exchanger solution. Okay, next one. Now, today's session is more about energy recovery device. And now I would like to shift the discussion from who we are to why energy recovery matters. Now, the theme of the webinar is avoiding the cost of doing nothing. Over the next 30 minutes, we will look at where the energy is lost in reverse osmosis system, why it matters, and how this energy can be recovered to reduce the operating cost of the RO over the life cycle of the plant. Before we go deeper into the discussion, I would like to understand the audience profile. I can see so many people have joined us, in this session. So I think it is the perfect time to launch a poll. And this poll will take only a few seconds of your time to respond. And your responses are important to help us understand, the audience profile and to keep the discussions relevant for you. We're launching a poll questions now. So the poll question is, do you have RO plants at your site? Please select the option which describes you the best. Yes, one plant, you have several plants. No, you don't have any plants, or you build the RO plant for others. We'll wait for 10 to 15 seconds so that you can answer, and then we will publish the poll results. So far, we are seeing a lot of responses have came. 120 people voted so far. We are waiting for a few more to respond. Okay, let's publish the poll results. approximately 40% of the people are saying that yes, you have the plant, and then there are people who are saying that we build the plant for others. So thank you first of all for participating. This is such a diverse audience, of end users, OEM and EPC partners and consultants joining us today. And let me tell you, your decision matter and are relevant because your decision influence the performance of life cycle of the plant in a different way. Now, let us go deeper into the discussion and understand how. In the meantime, I just want to ask you that some of your questions will be answered as we go along the way in the session. So please stay with us till the end. And during the session, if you have any questions, please feel free to drop them into chat box. We will answer those questions later, when the session ends. And if there are certain questions which are not answered, maybe we'll come back to you personally with those responses. Next slide. Now, whether you operate a plant, you design a plant, or you build a plant, okay? Next, this slide is very, very important for you. And why? Because in the reverse osmosis process, traditionally, the reverse osmosis plants are designed to recover water. But what happens to energy? But typically, in any RO process, you see high pressure pump pressurizes the water or sends the pressurized water into the membrane array. Now, membrane array separates this feed water into permeate, which is eventually a product water, which leaves at low pressure, and a reject. Now, reject stream, however, leaves the membrane process with most of the pressure generated by this high pressure pump. Now, of course, there are some losses across the membranes and piping. However, most of the pressure goes in the reject. Now, when this pressure goes in the reject, this simply hits the brine control valve, and all the available energy in the reject is lost. Now think of this way, we have already paid to create that pressure. We have already consumed the electricity to generate it. And then in many systems, we simply send it to drain. This is the hidden cost we are talking about today. And one thing we have learned over the years that, water and energy are deeply connected. The more water we want to recover, the more energy we generally need. And that is called as water and energy nexus. Now, the amount of energy recoverable depends on the hydraulic recovery or the recovery of the system. So if you have a plant which is designed for 85% recovery, 15% energy is available in the brine, and that 15% energy is getting wasted. Whereas if the plant is designed for 75% of the recovery, 25% of the energy is getting wasted. And lower the recovery, higher the losses across the RO system. So takeaway is very, very simple. Like I said, RO plants are designed to recover water, but are we recovering the energy which is helping it to produce? That is the hidden cost. Now let us understand the capex opex comparison between the RO plant through an example. Next slide. Yes. Now, this is a very simple capex opex example. And this is why this is important, because whenever a new RO system is planned or a facility is planned, the first discussion or first question is usually around the capital cost. What will be the project cost? Now, this question is very, very important. Not saying no, but I think that is just beginning of the story. When you actually commission the plant, the capex is paid once, but the operating cost stays with you forever for next 20 to 25 years when you're going to operate the plant. Now, if you see this example, in this example, capital cost is compared with the operation cost for a period of 10 years. So why we have used the 10-year evaluation period? Because probably the region where we are, this is a practical evaluation period considered in many, many projects. Now, as you can see, capex in this section only contributes to less than 25% of the cost. Everything else is OPEX. Now, if you further break down this OPEX, you will see that electricity typically contributes to 40 to 60% of the operating cost. Now, that makes power or electricity single largest controllable cost in the reverse osmosis plant. So the message is very, very simple. CapEx is something that you are paying once, but OPEX is something that you are paying every day till you operate the plant. And every decision today we make has a life cycle cost. And choosing not to recover this energy also has a cost. And this is the cost of doing nothing we are talking about, which is theme of our webinar today. Next slide. Now let us look at some customer success stories who have already installed these energy recovery solutions and how it has helped them to recover the energy and how basically these energy recovery devices are helping them to save money in real operating condition for the life cycle of the plant. Now we'll first start with the Indian example. Next slide. So this is our first example, Ranitech CETP in Ranipet, which is near Vellore, Tamil Nadu. So this plant treats a leather industry effluent where water quality is very complex. Now, what makes this case study interesting is that this customer has installed a turbocharger solution in 2011 and 2012, long before many people would have even thought about installing energy recovery device in wastewater applications. Later, when zero liquid discharge regulations became stringent, then a brine concentration plant was installed along with a pressure exchanger. Now today, both these technologies are operating at this plant successfully for last 10 years pressure exchanger and over 15 years turbocharger. The combination of both these technologies is helping the customer save 10 lakh units of electricity every year. Now, for those of you who are joining from overseas, this is approximately 1 million units of electricity per year. Now, at the prevailing cost of INR 9 rupees per kilowatt, this is approximately 90 lakh rupees per year energy consumption or energy saved, worth energy saved, which is close to 94,000 US dollars annual saving. Now think of it, for 20 years life cycle, if the power cost remains same, the value would be close to 18 crore or maybe 1.89 million. That is a huge number, okay? And this is the forward-thinking approach that this customer has taken. And this is what we want to tell you that, by recovering this energy, we can avoid this cost of doing nothing. Next one. Now, let me share another example. Now, why this example is interesting. Now, this example is coming from a municipal reuse application. Now, many of you know that municipal reuse applications are typically low pressure. So the customer is located in Belgium. The plant was recently commissioned in 2025, and it shows that the energy recovery can be quite valuable even in this low pressure application. But this is a very small capacity plant, 1.3 MLD or 1300 meter cube per day, operating at around 70 to 75% recovery. Now, by installing the low pressure PX in this plant, the customer has reduced the operating energy consumption by 23%. Now, even if the operating pressure is very low, from 6.7 bar to 13.9 bar, the payback is still less than 3 years. Again, key here is to look at the investment through the life cycle of the plant, and this is what is important. And as we see, municipal reuse is also growing in India and also across the globe. And we are seeing so many reuse opportunity where treated sewages are being reused to non-portable applications or even supplied to the industry. So these type of example to a scale which we are seeing the reuse are going to be very, very important and going to set the benchmark. Next slide. Now, we have
just 1 second before, it looks like some people can't see the slides. Could we maybe just restart the slides sharing real quick?
Is it something that they are not able to see now, or maybe for from the initial session itself when we started talking?
No, I think some people can see it and some can't.
Okay, so let's maybe reshare it so that everyone can see it.
Yeah, so hopefully everyone can see it.
So let us know your feedback once you are able to see it. Maybe some places, it is bandwidth. And nowadays it is rainy season in India, so I can understand maybe why they are not able to see it.
I think it's back up again. Hopefully it's visible to everybody now.
Yeah. So those who are not able to see it, can you confirm that you are able to see it again now?
Okay, it looks like some people are saying they can see it.
Perfect. Thank you so much. Thank you. Thank you. Okay. So now let's get into the solution part. Now we have understood that, okay, what is the problem? What is this cost of doing nothing? And we have also understood that how energy recovery has helped some of the customer to recover that energy and how they are getting benefited. Now let us talk about the solution part. Okay. So now before we go into the solution, I am curious to know, and maybe this is the right time to probably launch a poll to check that everyone is able to see the screen as well. That we are going to conduct a poll. Again, we need your responses, and this poll is again very simple. Before today, have you heard of energy recovery devices? So you will see some of the options coming in front of you, and if you have, say yes, I know them well. If you have heard of them, say I have heard of them. No, if you have not heard of them, tick that no box. And then if you're already using it, please, tick that, you are already using it. So we'll wait for 15 seconds for your responses. Yeah, I can see 105 people have responded. We'll wait for 5 more seconds so that people can log in their answers. Okay, all right. Can we publish the poll results? So I can see the poll result. First of all, again, thank you for your responses. It is helpful to see the mix of audience experience. I know some of you have already used it. And for those of you who are already using it, I hope the sessions gives you additional insight to different design configurations for industrial reuse, MLD and ZLD application. And if you have only heard of them, and this is your first introduction, don't worry. Over the next few slides, I'll explain how the technology fits into the RO system, and most importantly, how it helps the customers to reduce the energy consumption and operating cost. And by end of the session, you will understand that what an energy recovery device does and why it has become important part of modern RO design. So let's begin with the technology which has become the global benchmark of energy recovery, that is pressure exchanger. Next slide. Now, as explained, and maybe before we move into, this industrial or maybe wastewater applications, let me briefly, take you through the pressure exchanger part. And pressure exchanger, anyway, I have discussed that, we have proven ourselves in the seawater desalination space. And for more than 30 years, this technology has been a benchmark in the seawater RO. Every day, millions of cubic meter of drinking water is produced using this technology. And maybe many of you may be asking why this technology has become the benchmark. So let me maybe take you through a quick example, quick run through of how the technology saves the energy. Now many of you are aware that desalination plants operate on high salinity application, typically very low recovery, 40 to 45% recovery, some cases 35% recovery. So in this case, you see, because of this lower recovery, higher reject volume leaves the membrane process. Now, for the simplicity, I will take the example of 40% recovery. Now, let us imagine a seawater desalination plant designed for 40% recovery. That means 40% is your product water and 60% is your reject water, which leaves the membrane. Again, reject water carries a lot of pressure. So if you do not install energy recovery device, the available energy would otherwise be wasted. Now, what pressure exchanger does? Pressure exchanger being isobaric design, the reject water comes to the pressure exchanger from one side and basically transfers the energy to the other incoming feed water stream, which is of a similar volume. Now, when the reject pressure enters into the PX, it basically transfers up to 99% of the energy to the low pressure incoming feed water stream. So basically what you are doing now, 60% of the reject stream, the energy which is there in the 60% of the reject stream is basically being recovered through pressure exchanger and a circulation pump. And balance, part is naturally driven by the high pressure pump. So in this case, instead of designing the high pressure pump for 100% of the flow, you will design this high pressure pump for only 40% of the flow, because 60% energy is being recovered through the brine part. Now, in this case, most of you, or maybe people who are not aware, they may ask, hey, what is the role of a circulation pump? So basically, job of a circulation pump is very, very simple. This is to offset the losses which are happening in the membrane process, piping, and pressure exchanger. So circulation pump, nothing but, it takes the high pressure suction from the pressure exchanger and boost it by 2 bar, 2.5 bar to make up for the losses, so that high pressure discharge and, the water which is recovered through this process is basically, meets together and goes into the membrane process. So in this case, what we are doing, we are reducing the work which is done by the high pressure pump, and naturally the capacity also goes down. So for a 40% recovery case, high pressure pump recovery goes down by 60%. And because most of the energy is recovered, so the OPEX saving in this case is up to 60%. That is a huge number. And because of these things, you see year on year, seawater desalination plants are becoming very, very energy efficient. I hope this explanation has served the purpose why the pressure exchanger has become an important technology. Now, based on this success, the technology has opened doors for other applications. Now, these other applications being municipal reuse, industrial wastewater reuse, MLD and ZLD applications. So let's go on to the next slide. Yes. Now, this slide shows the pressure exchanger family, which has grown beyond desalination. Now, you can see, we have a dedicated pressure exchanger for low pressure applications, which are, less than 31 bar. We have a dedicated PX, which we have anyway for last 3 decades or more than 3 decades, which is designed for 83 bar. And ultra high pressure PX can handle 124 bar pressure. And you can see that low pressure PX is available from 6.8 cubic meter an hour flow, and it can go up to 59 cubic meter an hour. So for bigger capacities, naturally you can install multiple modules in parallel. And if you look at the ultra high pressure RO applications, where eventually the water is concentrated, and when it comes to the ultra high pressure application, the flows are very, very low. So ultra high pressure PX can be used from 2.3 cubic meter an hour. That's the smallest flow, and maximum flow is 56.8 cubic meter an hour. So in short, whether you are designing a municipal reuse plant at 8 bar or an ultra high pressure RO, which is designed for 100 bar or 110 bar, there is now a pressure exchanger solution available for this range. Now, for those of you who are seeing the pressure exchanger for the first time, you will notice from the image which is on the left hand side that there is a pressure exchange process which is very briefly explained, and this is basically the cutout view for your imagination that how the pressure exchange process happens. And in next minute or so, I will try to cover, maybe touch this explanation how the pressure exchange process happens, so that for those of you who have not seen and the pressure exchanger, at least you understand it. So now let us look at the blue stream. That is the low feed incoming water which is coming from the feed side. That is typically cartridge filter outlet. And then there is a red stream which is coming from the RO reject. Okay. Now both of these stream goes into the pressure exchanger from the diagonally opposite direction. They enter the rotor duct. Now rotor duct, basically rotor has small longitudinal ducts inside it. So when water enters the rotor ducts, rotor rotates. Each duct is basically filled with high pressure reject. Now when the rotor rotates, this basically come in front of the low pressure incoming feed water, and basically pressure is directly transferred into the process. So in simple words, one stream gives the pressure, other stream receives it. So basically high pressure stream gives the pressure, and when it hits the seal phase, it has lost all its energy, and then it is coming in front of the pressurized low pressure stream. And then that pressurized low pressure stream pushes that water away. So as you can see from the image, RO, reject is coming from one side and even going out from the same side. And incoming feed water is coming from one side and going from the same side out after, recovering the pressure. Now, I have been telling why pressure exchanger is high efficiency. Now, this direct exchange basically allows the PX, and the way it is designed, to recover maximum possible available energy in the reject. Now, because there is no barrier, there are very, very small losses around these devices. And because of this direct exchange process, very small amount of mixing is inherent to this process, but it is very, very negligible and it has no measurable impact on RO performance. Next slide, please. Okay, now, let us look at how these pressure exchangers are installed into multi-stage design. Now, we know that seawater desalination or high pressure ROs are most of the time single stage RO design. So we know how to integrate the pressure exchanger into single stage design. We have learned it. Now, talking about multi-stage RO design, and multi-stage RO design typically have two configurations. On the left-hand side, you are seeing the classic design, two-stage without any interstage booster. And on the right-hand side, you are seeing a two-stage design with an interstage booster. Now, in both the images, you will very clearly see that pressure exchanger is installed in the RO reject. And it is basically transferring the water to the incoming feed water stream, which we just discussed. Now, in the left-hand side, basically a circulation pump is needed to make up for the losses. And on the right-hand side, you are not seeing any circulation pump because with the interstage booster pump, you are already pushing extra energy to the membrane array. So in this case, your reject pressure is typically higher than the high pressure, pressure which is going to the membrane array. So in this case, you do not need an extra circulation pump to make up for the loss because the extra pressure is available. Now, this arrangement, whether a circulation pump is needed or not, this depends on the feed water salinity, the recoveries you are working at, and typically the hydraulic design that you are following. So based on that, my message is that pressure exchanger can be integrated into both type of configuration. Now, if you have a three-stage design, so pressure exchanger will be installed in the third stage reject. If you have a four-stage design, which I have seen typically in textile industry, even pressure exchanger can be installed even on that fourth stage as well. So the general rule of thumb here is, now you would have gauged it by now when I was explaining the seawater desalination process. In pressure exchanger, your total permeate flow becomes the high pressure pump flow, and your reject flow becomes the flow to the pressure exchanger. This is a very simple general rule of thumb I want you to remember. So just in case you are designing a plant or you want to calculate your energy savings, which we are going to see in coming slides, this rule of thumb is going to be very, very important. And before I move ahead, I just want to talk about one important point. A pressure exchanger has the ability to handle salinity variation. Now, this you may not see in the seawater desalination, but for the wastewater application where effluent characteristics are changing dynamically, this is a very, very important message that I want to convey. Also, in some cases or in effluent treatment plants, continuously maintaining 5 micron filtration requirement is not very, very practical. So pressure exchanger by default, by its design, can tolerate particle size up to 20 micron, okay, making it more suitable for most of the wastewater applications. So takeaway of this slide is very, very simple. There are different ways to integrate the pressure exchanger into an RO design. So the point is, after integration of the pressure exchanger, the system not only recovers water, but it also recovers the energy which was otherwise getting wasted. And that is the modern RO design we are talking about. Modern RO designs are energy efficient, low OPEX, and lower carbon footprint. That is the need of the hour. Next. Yes, another type of energy recovery device, turbocharger. The turbocharger are there in the industry even for a longer time. And nowadays, the use of turbocharger has become very, very niche. And this niche use is typically maintaining the high interstage booster, pumps. So we look at how the turbocharger replaces the interstage booster pump, and what is the, that sweet spot where turbochargers can be used. I mean, I'll just, speak of a general rule of thumb where we have experienced that maybe for these cases, turbocharger becomes a better option. So when to select turbocharger, I think I will just speak in next slide. Go on next, please. Yeah, so simple two-stage design. Now you are, in the image that you are seeing that there is no interstage booster pump. There is a turbocharger installed. Now what this turbocharger is doing? Turbocharger is recovering energy from the RO brine and giving it to the stage 2, the interstage, the stage 2. Now how it is doing it? So basically, on the right hand side image, you will see that turbocharger consists of a turbine impeller and a pump impeller connected by the common shaft. Now, high pressure reject basically enters the turbine and causing it to rotate. And because of this rotation, the energy is transferred, through the shaft to pump impeller, which boosts the interstage feed, before it enters the second stage. Now, in short, the turbocharger converts the hydraulic energy into mechanical energy, and then mechanical energy back into hydraulic energy, which is eventually the boost pressure in simple words. Okay. Now, turbochargers are best suited for application, and this is again a general rule of thumb, are where recoveries are very high, let's say 75% and above, and interstage booster requirement is 10 bar or maybe more than 10 bar. Now in those cases, they can replace the pump, and it could be a capex neutral option in some of the cases. Okay, and turbochargers are available from reject flows of 11 cubic meter an hour to 350 cubic meter an hour, designed for 83 bar pressures. Next one. Now, so far, we have covered the technology. We have seen how it works. We have seen where it fits in the multi-stage RO. Now, we have to come to the most important question. What does it mean in terms of actual energy saving? Okay. In the next few slides, we'll talk about a few examples how these energy recovery devices are saving the operating cost across different RO applications. Now, some of these examples which we have shown today or the calculation, they are real executed project, and there are a few examples which are a representative design calculation based on the real operating conditions, so that we can explain how these savings are basically coming up. So next slide, please. Okay, so let us begin with this tertiary treatment reuse example. Now, why we are beginning with this example? Because this example is something that we are seeing lot of tertiary treatment plants under discussion coming up, for bidding, and reuse is something which is becoming very, very common. Be it a data center, be it a municipal reuse, be it supplying the water to power plants. I think reuse is something which is going towards a place where now we are accepting UF and RO application. And typically when we talk about these applications are big in flow and low in pressure. So this example is nothing but a 10 mld TTRO plant where feed TDS is 1200 ppm, designed for 75% recovery. Now in this case, if you see the plant, if you go without energy recovery solution, okay, you see the high pressure pump consumes only 164 kilowatt of electricity. Now in this case, the high pressure pump is designed for full flow. Operating pressure is 12 bar. Feed pump remains the same. So the total energy consumption is 221 kilowatt. On the right hand side, after integrating the pressure exchanger, so as per general rule of thumb, the permeate flow becomes the flow to the high pressure pump, which is 312 cubic meter an hour. Pressure remains the same. And then you add a circulation pump, which is basically boosting the energy or the pressure which is lost in the membrane process and PX. After you add these numbers, you see without pressure exchanger, the energy consumption is close to 221 kilowatt. And with pressure exchanger, this energy consumption is 189 kilowatt. That is roughly 32 kilowatt hour saving. So if you multiply it by 24 hours of operation and 350 days by 9 rupees, which is typically the power cost in most of the cases, it is basically saving 24 lakh rupees, which is close to $23,000 every year. But this is not enough. Now, if you look at life cycle cost, I would like you to look at this example from 3 different perspectives. Now, first, from the perspective of an end user. Now, if you are an end user and if you are saving 20 lakh rupees every year, in 20 years, it can be 4.9 crores or 4.8 crores if the power cost remains constant. So for those of you who are joining from overseas, that is roughly close to 575,000 US dollars over 20 years. That's the cost of doing nothing, we are talking about. If you are a consultant, there is an opportunity to incorporate a proven model solution into the specification. And this is eventually going to help the life cycle cost of the plants. And if you are the OEM and EPC today, many of you are aware and many of you see, even in the industrial projects, there is a power loading or specific energy consumption guarantees are required. So this is something that can help you optimize your design. And even in some cases, there is a kilowatt threshold written where you have to use a low tension motor or a high tension motor. And for this project, it was very clearly specified that for motors going more than 160 kilowatts should be high tension. Now, if you see this example, without pressure exchanger, the absorbed power is 164 kilowatt. With pressure exchanger, the absorbed power is 123 kilowatt. So this answers your question that integrating a pressure exchanger has also lowered your capex by converting this HT motor into the LT motor. That's the advantage that you have. Next one. Again, medium-sized plant, 4 MLD, 6100 ppm TDS, designed for 65% recovery. Now, in this case, again, you look at the high-pressure pump, kilowatt is close to 120. If you look at, the pressure integration case, the kilowatt rating goes down to, 57, 58 kilowatt. Net saving of 31 kilowatt every hour. So if you multiply it by 24 hours of operation for 2 skids and 9 rupees power cost, close to 47 lakh rupees saving in the power every year, and which is close to 45,000 US dollars. And even for such a medium, capacity plant, it can really deliver attractive financial returns if you look at the life cycle cost of the plant. So that is another example for you. Next one. Okay, turbocharger. We have seen turbocharger, right? You have heard about it, that turbochargers are best suited for high recovery application and cases where interstage boost is more. And maybe for customers who are very tight on capex, this could be one of the solution which can be implemented. Turbocharger straight away replaces your interstage booster pump in most of the cases. And you can see that, in this case, on the left-hand side, interstage booster pump was consuming 27.72 kilowatt. It's 28 kilowatt. And when you install a turbocharger is basically recovering energy from the brine and giving adequate boost pressure to the stage 2. So now you do not have any electrical load here in the list. And you are saving typically close to 21 lakh rupees or $18,000. And most of this turbocharger case is a capex neutral, because anyway you would have bought a pump, a VFD, and electrical system. Instead, turbocharger works out to be a very good capex neutral solution here. Next. Yes, this is very important, and this is what we are seeing, and probably many of you may also be seeing this in the market, that zero liquid discharge, there is a regulation in India, and it is already implemented at certain places, and those places, the RO recoveries were limited to a number, maybe 90%. And there are some regions where the recoveries are higher. But why the customers were not able to concentrate the water beyond this level? Because the ultra high pressure membranes were not available. And since last few years, 3, 4 years, 5 years, the whole ecosystem around ultra high pressure RO has shaped up very nicely. Now you have ultra high pressure RO membranes, you have pumps, you have membrane system, you have a lot of, the whole ecosystem is developed. Now, in this case, many of you already know that evaporation is one of the costly process, and it basically consumes a lot of electricity as well. So recovering this brine, before going to evaporator by ultra high pressure RO is one of the solution many customers are implementing today. And if you implement the solution, so the net liquid which is going to evaporator is basically coming down, and ultra high pressure RO is something that you can operate at, a very, very lower operating cost. Further, if you integrate energy recovery devices, it basically, again, reduces your operation cost. Now, let me maybe take an example here that, in seawater desalination, the operating pressures are 55 to 70 bar. And in ultra high pressure RO, these operating pressures could be 90 bar, could be 100 bar, could be 110 bar. So recovering that energy becomes very, very important. And now if you look at this example, which is there on the screen, for such a small 400 meter cube per day system, 90,000 is the feed water salinity designed for 35% recovery. Without energy recovery device, you would go for a full capacity pump. At 110 bar, it would consume 82 kilowatt of electricity. Whereas if you go with the pressure exchanger, this high pressure pump capacity goes down by 65%. And now for the same pump, you are consuming 29 kilowatt. That is a significant reduction in the power. So roughly by adding pressure exchanger, you can save 52 kilowatt hour, multiply by 20 hours of operation. That is 1000 kilowatt every day for such a small 400 meter cube per day system, which translate to 32 lakh rupees or 29,000 US dollars for people who are joining overseas. So this is something really implemented on the ground in India, a UHPRO of slightly bigger capacity, and these examples are real and becoming very, very important to the end customers. Next slide. Yes, very, very important. And probably in next 3 to 5 minutes, I am going to explain these few bullet points that you are able to see on the screen. Now, many of you may be already thinking that, hey, look, okay, energy recovery devices are for new systems, fine. But what about, the existing system? There are thousands of systems which are already installed, operating, and how do we go about it? So let me take you through this session. Next one. Okay, now I would like you to think about a plant. If you are a end user operating the plant, or if you are a OEM EPC who are again operating the plant, if it is part of your contract. Now you can ask yourself these 5 questions. That is your plant is already recovering water? Your answer may be yes, but is it also recovering the energy? And since last few years, you see electricity prices have become the single largest operating cost, and we know why. Okay, because in many of the RO plants, energy is one of the highest, OPEX item. Okay, and further, these rising costs are becoming a challenge to the operations. And also, another question is many organizations have set their targets to reduce the energy emission, to reduce the carbon footprint. So if you are end user operating the plant, is sustainability goals becoming part of your business? These are the questions which are very, very important when we meet and talk to our customers, and this is how even they evaluate some of the solutions. So if answer to these questions is yes, so then you will have a question, hey, can my plant be upgraded? And what is the investment needed, and what is the saving, and how can I lower the operating cost? Okay, so the good news is that yes, existing RO plants can be retrofitted, and they can be upgraded with the energy recovery solutions. Also, sometimes upgradation or retrofit is necessary because you might have designed a plant 5 years back on some water quality, and today maybe that water quality is not coming. Either the salinity TDS is higher, TDS is lower. You might have different challenges in the operations. So even this can definitely value add to the solutions that you are looking. Now the good news is that you can retrofit the plant. Yes, but you will be curious to know, hey, how much cost I will save. Go on to the next one. Now, before I talk about this slide, I want to again run the last poll of today's webinar, and I'm curious to know what you think about it, and we want to know your answers. Okay, and the poll question is that would you like to know how much energy cost that you could save in the existing RO setup? So there are 3 options that you have. Yes, please send the details. B, maybe share some info, and C, not right now. So we'll wait for 15 seconds, 20 seconds to for you to log in your answers, and let us see what the audience has to say. Yeah, poll results are coming up. 85 people have voted so far. We are waiting for, yeah, this is. We'll wait for 5 more seconds, but we know there is a big option which is being selected. Okay, can we publish the poll results? Yeah. It is great to see many of you are interested in understanding saving potential of your RO plants. I think that was eventually the case. And good news is that you don't have to estimate it on your own. Okay, so if you can send us some of the information of your existing plant, the design capacity, the operation parameters, the flow rate, the pressures, the TDS, the recovery range. If you are operating the plant at any recovery range, increasing and decreasing the recovery based on the production, the water quality. If you send this information to us, we'll help you to basically tell you that, okay, this is the amount of energy which can be saved in your plant. And I'll just share the contact details where you have to send this information. Next one. Okay, Power Model Pro. Now this is something which is for all, whether you are an engineering company, whether you are a consultant. We have a Power Model Pro software available, where you can design and select these energy recovery devices. You can get your result, how much energy you are saving, which type of energy recovery device is giving you better saving. You can get your results, and all this information is available on this cloud platform. So you can go to energy recovery website, log into this Power Model Pro, and you will be basically provided access. And if you have any questions and you want to know more about this Power Model Pro, do reach out to us and we'll help you, to explain how you can use the Power Model Pro. So the important point here is that, we have also, for OEM, CPCs, and consultants who are working, we have made sure that, they are also empowered to select these energy recovery devices. And this remains a common knowledge that, hey, look how easy it is to select these solutions, because your RO system is already designed. And now you just have to make sure that, you have the energy recovery solution designed to make sure that you are, recovering the best possible energy from that system. Next. And this is something which is very, very important, right? Go on to the next one, please. See, behind every project, I think there is a strong team which helps you execute the project. And at Energy Recovery, we support our customers through the life cycle of the project, be it from specification, to design, to commissioning, and even the aftermarket, support. Okay, so whether you are working on a desalination project or an industrial reuse project or MLD ZLD or retrofit, this is the regional team that you have. You can see name of salespeople, you can see name of technical person, and you can see name of the aftermarket person. So feel free to reach out to us. Okay, we'll be happy to help you. And if you have any, the assessment request, please send out to the sales team. I am Ajay. I'm handling India and Australia. Mayank is handling India, Australia, and even the whole Asia Pacific region. Ashik is based out of Southeast Asia and handling Southeast Asia and Japan. So if you are from Southeast Asia, you can contact Ashik. And if you are joining from any other territory, please feel free to reach out to us, and we'll connect you with your local partner. And lastly, next one. This is regional team as well. To provide faster support across India, we have 3 reps. We have Pure Water in Mumbai, Mr. Sanjay Mehta. You already know him well. You can reach out to him on this mobile number. Gurneer, Mr. Amit Chaudhary, he's an industry veteran as well, based out of New Delhi. And Senkar Technologies in India South, where Mr. Karthik Balaji and his team are also working with a lot of customers. So if you want a faster support, these guys already, please feel free to talk to them, to work with them, and make sure that you get the right support. And you can also contact us anytime. Next. Yes, over to you, Ashik. We are open for questions.
Yeah, thank you, Ajay. So I hope you all found that informative, and this short introductory webinar at least evokes a fresh perspective on how RO systems should be designed. This is a change in thinking that needs to happen at the moment as a collective water community within us. especially as water and RO systems become more and more impactful on the availability of water in the rapid pace that of development that our region is currently going through.
Yeah.
And again, this is where we can help. Majority of the time, all we need is just to have a look at the RO membrane projections, and we can provide the technical guidance to incorporate the ERT into our system. Now, let's go through some questions that we have, and if we aren't able to address all the questions during the webinar, we'll definitely reach out to you personally. So Ajay, there was one interesting question I think relates back to the part where you had the varying salinity fluent that you talked about. So the question is, which is better when the salinity is varying, whether it's a PX or ERT? I'm guessing he meant turbocharged.
Yeah, the ERT is nothing but turbocharger. Some people call energy recovery turbochargers. I think, see, for salinity variation, we see PX, holds very good, because in PX, I think important thing is, like you have seen the municipal reuse example, even the salinity is varying. Okay, pressure exchanger. So the simple philosophy behind the pressure exchanger is, and let me take this example, and maybe don't quote me on the efficiency part here, but for example, across the pressure exchanger, we have seen that the maximum pressure drop, again, as a worst case, is 1 bar. Okay, so if you are feeding 60 bar pressure, for example, you are recovering 59, so that is more than 98% efficiency. If you are feeding 10 bar, you are recovering 9 bar. So eventually, in the pressure exchanger, basically the net pressure drop remains, it can be lower, but the maximum pressure drop, let us say, is 1 bar. So point is, pressure exchanger is still able to recover the energy to the best possible extent. Turbocharger is nothing but pump impeller and turbine impeller. So basically it has a curve, like the best efficiency point. So turbocharger has to be designed for those cases, but definitely PX provides a better operational flexibility for those varying salinity conditions.
And I think another interesting question that I see here, I think, can we share a thumb rule to determine if the PX is feasible or not in any particular RO?
Okay, so thumb rule means, is it the selection?
Whether or not a PX is feasible to be installed in that RO. I think that's the question.
Okay, maybe the way I understand this question, maybe I have some backup slide. Maybe if you can go next slide, maybe where you see the PX flow table. This is something which is a most common question. So naturally, this backup slides help. So pressure exchanger contains several models. Okay, from the chart, you can see there are different models for 31 bar, different model for 83 bar, and different definitely models for the ultra high pressure. And each pressure exchanger has an operating range, which you can see on the table. So simply, if I have to tell you, if you have to select a pressure exchanger, very easy. 10 seconds, you can do that. So for example, if your RO plant has a reject flow of 50 cubic meter an hour and basically operating pressure lower than 31 bar, which one you will select? So if you see, there is a PX L260, which can handle the reject flow between 40.9 to 59 cubic meter an hour. So that is your selection. Very easy. Okay. So pressure exchanger selection that way is very, very, very easy. Now, depending on your hydraulics, like I said, whether you need a circulation pump or whether you have an interstage booster pump, this is something that can be part of your calculations. But selecting a pressure exchanger is very, very easy.
And I think we have maybe time for one more here. And again, we'll get back to everyone who we didn't get their questions answered to. So what feed water quality limitations exist for suspended solids, scaling potential, or any fouling for the pressure exchanger itself when the pressure exchanger becomes unsuitable?
Yeah, no, I think this is good question. I think, like I said, filtration requirement and salinity and the scale part. Scale part is something which is interesting, right? I think we run those anti-scale and projections to make sure the scale doesn't exist. However, there are cases where, we have seen that, the kind of system has, developed some scaling. So for those cases, I think some operation smarts that needs to be done, that, keep flushing the system intermittently, and make sure your anti-scalant is okay, and your pre-treatment is designed to handle those salinity variations. Because see, eventually, if you protect your membrane system from the scale, naturally everything else will be protected. Pressure exchanger is nothing but the downstream, part of it. So if your RO system is protected, naturally the PX is protected. But for intermittently, if you are seeing some cases, so maybe it is better to troubleshoot where the salinity variation is, why, this is, the scale is happening, and basically address those problems.
Sure. And yeah, so I think one more was who do they go to for any retrofit opportunities? But I think you can reach out to anyone in that contact list. We all work as a team, so any one of us could be a initial contact point that you need, and we'll definitely route you through to the right person. So thanks a lot for that, Ajay. I think we are pretty much on time right now. I hope everybody found this informative, and if you have any questions, feel free to reach out to us, and I hope you have a good day ahead. Thank you very much.
Thank you so much, everyone. Thank you.
Thank you.